Hello everyone, and welcome to PyCampus. Welcome to our PyCampus networking events. We haven't had the opportunity to do many events during the COVID, during the last 2 years. Many of those were remote with a great attendance, and that I think is one of the first time that we're getting together. And it's a big pleasure to see this big audience coming and not enough seats for everyone. Next time we do it in the pool as the big parties we were doing a few years ago. We didn't expect this many people, but we're so happy to see so many because it's a special event today. It's something that we do care a lot about, a research that truly is connected to the vision that we have here at PyCampus. And by the way, machine intelligence meets human creativity. I cannot think about a talk that make these things closer. So super happy. Just for those of you that have never been in PyCampus, very short intro where we are. So I'm Marco, the founder and CEO of PyCampus. And so PyCampus is a venture fund. It's a venture fund that invests in AI applied startups. And we provide pre-seed and seed funding, so which means that we invest very, very early in companies, typically when the company is not even there. And we give money to researchers before they fund the company or just after they created the company. And mostly in the applied AI space. In exchange of that money, 50,000 or 500,000, we ask back from 1 to 10% of the company. And the business is very simple. We hope that that company will become the next Google. If they succeed, the founders will be very rich, and we will be quite rich. That's a simple business model. So as you see, the companies we invest are basically everywhere. And with maybe some limitation in China, not because we don't like it, but because we're not good at investing in China yet, but I hope we will start soon. A lot of investment in Silicon Valley, in California, many here in Italy and in Europe. That's the area. We invested in multiple sectors connected to AI. Transportation is probably the most important. We invested in Andrew Curry that was working in creating the Tesla autopilot, and then created Level 5, another self-driving company that was sold to DoorDash, food delivery company. We invested, probably the most successful investment we have done is Boom Supersonic, a new supersonic plane that goes from London to New York in 3 hours 15. And that plane was possible, different from Concorde, because it's been modeled, everything by 1.2 million hours of computation. So basically a big, big model to predict everything inside the plane instead of using a wind tunnel. Boom, just a few months ago, announced that they sold 20 planes to United Airlines, and more are coming from Japan Airlines and China Airlines and many more. So we're talking about a multi-billion-dollar company. We have 56 companies. Unfortunately, they're not as big as Boom, all of them, but we have seen many incredible things happening, and especially in the area of human-machine symbiosis, where we build technologies, models that can help humans achieve great goals. The plane is an example. Simulating, getting ideas, building better planes is extremely powerful. Many of our investments are also in medicine, where we're working a lot in trying to help doctors to do better diagnosis, for example, or predicting what chemotherapy is best for a given DNA of a virus, of a cancer cell. So many areas here. What else? Why is super important, the talk that we're having today here? So you know, PyCampus exists as a part of Translated. So the first business I co-founded with Isabel in 1999 was Translated, and was one of the very, very first pure internet translation company that has been using AI since '99, so when really was not very cool. And we had, basically, if we were saying we were doing AI, people were not coming to buy our translations because they were feeling they were bad. So now it's quite the opposite, I will say. So Translated has been helping professional translators to do better translation, more creative and faster translation by creating these, what we call adaptive neural networks. These are models that predict the translation for the professional translators. They edit and fix the errors of the model, and the model learns in real time, and so adapts to the style and terminology of the translators, follow them. So it becomes their digital companion, really symbiotic with the translators. Translator became 3-4 times faster, and actually they produce much less errors. So something that worked very well, and actually, a technology that made translated the company voted by translators as the best company to work with in the world. So we love these kind of approaches because they're not just ethically nice, they're very, very interesting from a business standpoint, because you can take very large markets and make them 20, 30% more efficient. Translation is a $50 billion market. If you make people 20% faster and more creative, you created a $10 billion opportunity. And we love that, and we love to see other projects that are going in that direction. And mathematics is probably the hardest challenge we have. I was telling everyone the language was the hardest one. It's the most human thing. But now that I think, in fact, mathematics is probably even more complex. So having research to study how to solve mathematics by powering humans with great tools, the new calculators, that is incredible, and we're super happy of having Petar with us today. So I will give the microphone to Simone for another small introduction and the preparation and the invitation for our guest. Thank you, Simone.
So wait, I don't want to, okay. I don't know what I'm doing. Okay, that's basically my life. Okay, hi. So I'm an assistant professor at Sapienza. It's my really pleasure to introduce Petar. Actually, I've been following Petar's work since, well, basically since you started. You can say I'm a little bit of a groupie. Can I say that? And so when they asked me, okay, I mean, we invited him here. When they asked me, can you introduce Petar's work? I was kind of very, very anxious, and so the slides are kind of disconnected because it was really hard to me to find a cohesive way to tell you how much I enjoyed this particular work. Because I think that what they are doing, what also translated in this sort of machine humans companies are doing, are not just cool application of artificial intelligence. They're really, I think, the most interesting direction that artificial intelligence is taking today, and also the most probably interesting direction that artificial intelligence has since it was founded in a certain way. So forgive me for going very, very back in time, but if you think of the beginning of artificial intelligence, the artificial intelligence that we use today, okay, neural networks and these kind of things, if you find a starting point maybe in time, it could probably be cybernetics. I don't know how many of you know cybernetics, but it was this incredibly influential discipline that came out in the mayhem that was World War II. And it was basically focused on the idea of understanding how machines can be controlled, but also how machines can communicate between them. And immediately, also, if you think of a human as a very complex machine, what happens when you combine humans and machines? What kind of control and communication and command loops you can do? And and it's not surprising that in cybernetics, as in machine learning today, there are like highly heterogeneous people. Okay, many of you might know Norbert Wiener, who's like the father figure of cybernetics, McCulloch of the first artificial neuron. But I want to focus very, very shortly. Sorry, again, I don't know what I'm doing. On this guy, Ashby, is sort of forgotten today, but it was a very famous, very influential English neuropsychiatrist of the time. The second, let's say, father figure of cybernetics, incredibly well known. And if you want to know, he created a very funny machine. You can find also some videos online called the homeostat, which was a small machine built around the idea of feedback loops and homeostasis and all these things, which it's sort of eerily reminiscent of neural networks. It's like, for me, it's like the grandfather of neural networks, okay? So this is where all these ideas of neural network came from, also the diagrams, etc., and also the hype of neural network. At the time, this was supposed to be like the next closest thing to a human brain. But why am I bringing Ashby up? Because he wrote one of the most famous cybernetic books, An Introduction to Cybernetics. So again, this is really where all we're doing today in a certain sense started. And he was convinced that intelligence, it's not just a matter of symbol manipulation. Intelligence is a matter of searching and finding ideas, and in the middle of all this combinatorial explosion of ideas, finding those that have value. Okay, for him, this creativity, this intuition was the closest you could get to pure intelligence. And so for him, the real aim of cybernetics and all his work was creating these incredible loops to increase what he called intellectual power. So, okay, what we're going to see now, I don't want to put the hype too much. This is typically I tend to put it lower, but really what we're going to see is not just very cool application, okay, a sideway application of artificial intelligence, but it's the latest incarnation of an incredibly powerful idea that, I mean, has permeated the entire history of artificial intelligence. So I like to thank quickly also Fabrizio Silvestri here, because he helped us put in touch with Petar in inviting him here, P-Campus for hosting him, and I'll leave again, I don't know, it's incredible. There are 2 buttons and I keep, you know, I'll leave the floor to Petar for his talk.
All right. Thank you very much for the fine introduction and the very warm welcome here at the Pi School. And thank you also, Simone, for the very interesting introductory notes, which I believe I've learned something here just now, and I'll be looking up more of what Ashby has been up to when I'm done here. So, hey everyone, my name is Petar Veličković. I am a staff research scientist at DeepMind and an affiliated lecturer at the University of Cambridge. And today I'll be talking to you about, well, as you've heard in some of the previous expositions, some of our recent work on bridging together artificial intelligence and problem solving in mathematics. But I wanted to kind of expand the bubble a little bit and tell you about maybe what's the broader picture idea that makes me very excited about work like this. And as we can see here, I think it aligns really well with the tagline of the venue where we're at right now. So I'm going to be talking to you about the truly amazing things that can happen when human experts and artificial intelligence act in synergy, which is where I believe a lot of really awesome untapped potential actually is. So let's try to explore this a little bit. Now, probably I don't have to explain too much about the impact artificial intelligence already has on our day-to-day lives to the people in this room. There's a lot of really fantastic things that artificial intelligence can do already. They can perform really complicated control tasks, do game playing at a superhuman level in various domains. They can efficiently fold proteins, predict travel times in Google Maps, and predict future wind patterns for more efficient sustainable energy, to just name a few examples that we at DeepMind have also quite actively been working on in the past years. But I also wanted to just to make sure that everybody in the audience is at the same page on what these things are able to do, and on a high level, what are we able to do to them in terms of intervening on them and trying to explain what they do. I just thought I'd preface this talk with a little brief disclaimer on things that might be familiar to most of you, but it's still good to kind of have as a backdrop in your minds. So we think of artificial intelligence as the science of building intelligent things, more generally, and machine learning and deep learning are just specific subsets of that that are capable of learning from experience. Specifically, deep learning is so capable of learning from experience that it can learn directly from raw data almost without any human interventions. And the main reason behind these techniques work really well recently is because to program a computer to be smart is really, really challenging. But programming it to learn to be smart might be actually easier than that. It might be a more tractable problem because it relates to statistically extracting interesting patterns that live in data. And to illustrate that, I'm going to, just start off with the usual fun exercise. I'm going to show you a picture. There's no trick question here. What do you see in this photo? Yeah, I would say that I'm looking at a cat as well, and the many years of experience you've had on this planet have taught you that what you're looking at right now is a cat, right? Now, if I ask you, try to write a program that looks at a picture like this and tells me, okay, you're looking at a cat, well, you might say, okay, there are some very interesting characteristics that make this thing a cat. Like it has the big eyes, it has the characteristic ears, and so on and so forth. Well, you might try to then go away and write a program that does all of this, but I take your program and I raise you these counter cats, right? If you look at these things, and we as humans, when we look at them, we still are pretty confident that these are still cats, but they don't satisfy any of the criteria that I just outlined. And I hope you can see how programming a machine to be able to recognize a cat from pixels is basically a game of endlessly chasing your tail, because you can come up with more and more conditions on what makes a cat, and I can give you more and more counter cats that make the solution even harder to find. This is a good theme, because when we switch to maths, we'll be talking about counter examples quite a bit, right? So counter cats I thought were a fun way to start. And even just beyond that, they come in all different shapes, sizes, colors, and so on. Like, I can't imagine writing a program to actually do this recognition for me. So what we do instead in machine learning is we take this model, often called a neural network, that looks at the individual pixels of an image, and based on many, many pictures of cats, it somehow learns inside it what's the essence of being a cat, so it can predict as output, okay, what I see in this image is a cat. This is the essence of most computer vision systems you see nowadays. And for this talk, I don't really want to dive into the details of what these neural networks are learning, and for the most part, you can imagine them as a black box, and as anyone who works on artificial intelligence explainability will doubtlessly tell you, you wouldn't really be wrong if you assume that this is a black box. Like, we don't really understand what is captured inside systems like these, only at a very superficial level, okay? So if it's a black box, then how can it really help us draw conclusions about the program that's been learned inside? Well, there's two main ways in which you can try to intervene on a model like this. The first one is typically these kinds of systems, they don't just give you a straight up answer, they give you a probability of their confidence in that particular answer. So when you ask it, you can ask it, for example, how confident are you that this image is a cat, and it might give you a number like 97%. So this is the first type of intervention you can do. You can figure out how likely it is that you have this particular prediction from this particular input. And that's one way that we can interact with the model. Another interaction that you might imagine is we can try to look at the input space and ask ourselves, using some simple gradient saliency methods, what are roughly the parts of the input image that have excited the neural network the most, right? That have led to the most significant part of this prediction. And you might imagine for this cat image, such a method might give you these kinds of patches that highlight the cat's eyes, the cat's ears, and so on. Now, once again, anybody who works on AI explainability will quickly tell you that this is nowhere near being perfect. It can be hacked and adversarially tampered with in many, many ways. So nobody should really trust these kinds of predictions too much. But they are very simple interventions that, as I will show you later today, can already lead to very meaningful outcomes and significant results in an area as abstract as mathematics. So just because there are many problems with this doesn't mean we cannot do cool things with them already, okay? So, to kind of make the segue into maths, I'm going to take a slight switching of gears and a detour into graph representation learning, which is the area of machine learning I am currently working on. And that's what initially drew me into the maths project in general. And the reason why I like to study data that lives on graphs is because when you think about it, graphs are pretty much all around us, right? So the data that machine learning and AI nowadays typically works on, like images, speech, or text, is a nicely arranged grid-like data with a clear structure. But in many cases, the data that truly comes from the real world isn't arranged in such a nice, clear structure. So for example, chemistry and biology, from the basic building blocks like molecules, is constructed as a graph of atoms connected together by chemical bonds. And going as far as, the connectome structure in the human brain, which is how we biologically base most of our cognitive processes, is an interconnected network of neurons connected together in the human connectome. And beyond just the biology on various levels, also various aspects of human constructions are best represented as graphs, such as transportation networks. Here is the somewhat outdated picture of the London Tube map, because I believe they recently built a new line. But anyways, it can be best reasoned about as a network of stops connected together by lines of the network. And also here, an older snapshot of the Facebook friendship graph. Once again, social networks are best reasoned about using a graph of users and the various friendship connections that they make. So if you think about it, graphs are a very natural object to study, and in many ways the data that we get from nature very often takes this graph structured form. And this was my motivation for studying these objects. And maybe one of my most interesting previous claims to fame in this area is I took part in the team that within DeepMind used these graph models that process data that lives on graphs and deployed it inside Google Maps to tell you, when you ask Google Maps, I want to go from point A to point B, you typically get this kind of prediction that tells you how long it will take you to get from A to B. So the system that gives you that prediction, the time it will take you to travel, which billions of users use daily to make decisions on how and when to travel, is actually served by a graph neural network that we have developed internally at DeepMind. And this is now deployed worldwide, but already at the time of deploying it, where we did it in several cities, we relatively improved Google's previous best baseline by quite significant percentages. In some places like Sydney, there was over 40% relative improvement to what they previously did without graph neural networks. So clearly they can make a huge impact, and they are already like influencing billions of people on a daily level. Okay? But everybody who works with graph representation learning, with inputs that live on a graph, is bound to, at some point, process this kind of data. The molecule is a very natural graph-structured input, and it's kind of the ubiquitous building block of computational chemistry. And therefore, even if you're just studying how to build basic graph models, you're bound to try them out on biological data sets of these molecules. Okay? And one thing that you might ask yourself in a typical molecular classification problem is these kinds of small molecules. I think this one here is paracetamol, if I'm not mistaken. They're often used as drugs, as treatments for various diseases. So one typical kind of drug that we use very often in our day-to-day lives are antibiotics. So they're capable of inhibiting certain bacteria. And a very natural task, you might ask a graph neural network in this case, is I have this particular molecule. Does this molecule inhibit particular bacteria, such as Escherichia coli? And you can build big data sets of molecules for which you know whether or not they would be good antibiotics. So this is a well-defined classification problem that you can learn how to do. And it turns out that once you train a system like this, you can apply it on any molecule, including the molecules you haven't seen in your training data, right? And as we said, the model can typically give you a confidence score, right? It won't just tell you this inhibits bacteria, this doesn't inhibit bacteria. It will actually tell you what's the confidence it has in the bacteria being inhibited. So what you can then do is you can take a database of a lot of molecules that never have been tested for antibiotics, but are currently undergoing some clinical trials, which means you won't have to go through the whole clinical trial process again. So they might be used potentially as treatments for something else other than antibiotics. And you just run your pre-trained model on a lot of those molecules. And for some of them, like for this guy over here, the model might just end up giving a really large confidence, like say 99% probability that this inhibits bacteria. But no computational chemist ever studied this molecule in the context of antibiotics, simply because they will tell you this has a very weird structure. It's an unusual structure for an antibiotic to have, right? So nobody thought to explore this part of chemical space in the context of hunting for an antibiotic. In fact, this particular molecule was used as a potential treatment for diabetes, which is a completely unrelated thing, right? And okay, so perhaps if the model says there's a very high confidence, maybe this is worth investigating. Maybe we can take, say, the top 100 predictions of our model in this data set and send them off to computational chemists and see if this intervention helps them discover a new candidate drug for antibiotics. And it turns out that this molecule here that I showed you turned out indeed to be super, super potent as an antibiotic. And in fact, it was that weird structure, the fact that would never make a computational chemist think this is an antibiotic, meant that it had such a weird mechanism of action that it was capable of defeating even the bacteria that have evolved over the years to become resistant to all the antibiotics we pump into our bodies on a regular basis, right? So this was actually a super potent antibiotic, even against antibiotic-resistant strain of bacteria. So it was a super big find. It was published in one of the top journals in the area, Cell, by this team at MIT, led by Jonathan Stokes. And the repercussions and the sharing of this work have been quite big. Very quickly, it was reshared by Nature. And then beyond that, it was shared by the Financial Times and by the BBC. You might remember this. This came around February 2020, right before the COVID pandemic hit. I think because COVID kind of overshadowed it, it didn't get as much attention as it should have. But it's still one of the coolest applications of this graph representation learning, in my opinion. And you might have seen these titles at that time. Scientists discover powerful antibiotic using AI. Well, now you can know the AI was basically this graph neural network. And the way it was discovered was we intervened on the predictions of a model. And in collaboration with domain experts, we used that output of the AI system to discover a new potent drug in the area of the chemical space nobody thought to look before. Okay? So this hopefully gives you one example of a very simple AI intervention. Just check the confidence on a standard data set that can help make new discoveries in computational chemistry. Okay? And now that I've kind of set the stage for the kinds of interventions we can do, the areas of machine learning that excite me, I'm now ready to dive into the core part of this talk, where I want you to keep in the back of your minds the question, can we discover new structure in pure mathematics with the aid of machine learning? So first of all, maybe it's good to try to answer why do we even think this is a question worth attacking? Like, why do we think something interesting will come out of this? And I think one of, in my opinion, best reasons for why we should do something like this is because if you think about it, the study of mathematics might appear to be very rigorous and very abstract, but it doesn't just involve starting from a set of axioms and then blindly applying rules until you hit something, right? In reality, very often, if you ask any mathematician, they will tell you some of the most important results they've made have not been made by blindly applying logic, but by having a very specific leap of faith, some moment of creative imagination that led them to discover a result like that. And perhaps there's no better example of this than the mathematician Srinivasa Ramanujan, who, despite having no mathematical formal training whatsoever, was able to come up with these amazing conjectures that felt like they materialized out of thin air and they stunned the mathematicians of the time, right? So clearly there's some aspect of creativity and imagination that's unrelated to just mathematical training and blindly applying logic that leads to these kinds of discoveries. And another example, which is one of my favorites just because of the quote and because of how it aligns with what we did, is the work of this mathematician, Johannes Kepler. If you don't know about him, he's most famous for discovering the laws of planetary motion, so how the different planets in the solar system move around. And the way he arrived at this conclusion is by staring at years and years of astronomical data, like positions of different planets at different nights. And when he finally discovered that there was a very specific regularity in how these planets were moving, he's famously quoted by saying that he first believed he was dreaming, okay? So mathematics is not just about blindly hunting for patterns or blindly applying logic rules. There's a lot of creativity, there's a lot of imagination, there's a lot of dreams even, okay? And that we felt was something we could intervene with a machine learning system. So what if we had a carefully designed AI system that would allow a mathematician to go about their day-to-day work, and whenever they need to like zoom into a complicated object or investigate that object in more detail, that they would be able then to ask the machine learning system, hey, can you tell me something interesting about the object I'm looking at right now? And then the AI system would come back with some possible suggestions that then the mathematician can use to, maybe even in a virtuous cycle, eventually arrive at novel, interesting mathematical results. When we first asked some mathematicians that we talked to about this, about whether or not they believe this could actually work, I think the reception we got was reasonably skeptical, to say the least. Like, mathematicians were not that convinced that these kinds of interventions could really make any meaningful impact in their day-to-day work. However, 2 years later, and after a lot of intense collaboration with our mathematical collaborators from the universities of Oxford and Sydney, we actually have been able to use this blueprint to meaningfully intervene in two very distinct areas of mathematics, knot theory and representation theory. And the significance of our result was strong enough that the journal Nature decided to feature our work on the cover page a few months ago. and it also received quite a substantial coverage in the press as well. But beyond the fact that the significance of the result was recognized in this way, what's way more important, in my opinion, is the response we got from the anonymous mathematician reviewers who were specialists in those areas, and they read our paper to assess whether it would be a good fit for Nature. And the experts basically gave a completely opposite view to what we initially had as a skeptical reception. So first, we had reviewers saying that the paper marks the beginning of a new phase in the use of computers in mathematical research, and maybe most importantly, they cannot imagine a mathematician not using this method if it was available to them, because not using them means progressing much more slowly, okay? And beyond this, Marcus du Sautoy famously quoted that our work feels a bit like Galileo picking up a telescope and being able to gaze deep into the universe of data. Like we offer this precision tool that's allowing you to take a look into what's inside mathematical objects and help you progress further, even if those objects are very complicated. Okay? So now I would like to tell you a little bit more about our individual mathematical contributions and to kind of illustrate how we've been able to bring this virtuous cycle to life. The first area that we studied is knot theory. If you're not familiar with knots before, they are these embedded three-dimensional objects that look like this. They're not at all dissimilar from the knots you see in real life. The main difference is that the loop must be closed, so the knot actually doesn't have any ends in this case. And what we were interested in with our mathematical collaborators is to think about how is it possible to analyze knots. There are two different ways. Because a knot is a structure that crosses itself in various ways, you can study the algebra of those crossings, like doing various additions and subtractions on the ways the knot crosses of itself, which gives you an algebraic view into the knot. Or you can observe the knot, as I showed you before, as an embedded three-dimensional object and study its geometry, right? Its topological properties. And for many, many years, there haven't really been any connections known between these two views. There weren't really any hypotheses that these two views were connected. So with our mathematician collaborators, we wanted to study, does there exist any connection between the geometric view of a knot and its algebraic view, okay? So as you might imagine, we went away, we took one of our neural networks, and we tried to take a bunch of geometric quantities of knots, and from them predict a particular algebraic property of a knot, known as a signature in this case, okay? And it turns out that our neural network, which was a very straightforward multi-layer perceptron that looked at the various inputs of the geometry and predicted just since the signature is an integral property, it was just a simple classification task. And it turns out it had a very high accuracy. So a relationship was definitely found. And as we said before, just the existence of a high scoring accuracy can already be quite encouraging to the mathematician, because it will tell them that there probably exists something here. This is a connection you should probably study in a lot more detail. But that in and of itself is not enough to make advancements in new mathematical theories, because the mathematician needs to know what was the part of the input that was most important for the output. And that's where we start to investigate where are the cat eyes and the cat ears of this particular geometry, right? So we asked the model using simple saliency methods, so just to check which parts of the input gave the highest gradient when computing the output. And we produced a plot like this, which you have different geometric quantities and how much they influence the prediction in the view of the method. And it doesn't take a degree in mathematics to see that there are three quantities that are a lot more important than everything else, right? So what did we do? We took these three quantities and we told the mathematicians, hey, these three quantities are likely very important for the theory that you want to prove. So they took these quantities, the meridional and the longitudinal translation, and based on them, they went away for a few weeks and they came up with this formula for a new quantity, which they call the natural slope. It's a very simple combination of those two quantities, but it was obscure enough that no knot plotting software was able to produce this quantity. It just wasn't seen as that important. But it turns out, when you plot this slope against the signature, you get a very, very clear, almost linear fit. Like, it was possible to show that this slope was very close to 2 times the signature. So this was giving us a very clear beginning of a rule that would connect the algebra and the geometry of a knot in a very clear way. And in particular, our collaborators created a first version of a conjecture where they said that the error of this linear approximation is no bigger than the square root of the volume of the knot. Okay, and this worked for all the knots we've been able to generate in our initial data set. However, as you might expect, this did turn out to be just a conjecture, and if you try hard enough, you might actually break it. And the mathematicians realized that there are these classes of highly twisted, braided knots, which they could use to push this error term so far that the conjecture would not hold anymore. Okay? So this was our first somewhat dissatisfying result, but we never actually gave up because, you know, there's more of this plot to go. We revealed these three things that seem highly important, and indeed they do seem to be highly important. But if you look at the rest of the properties, you know, even though they're insignificant compared to the first three, there's still this group of three quantities, the short geodesic, the injectivity radius, and the cusp volume, that seem more important than everything after that, okay? So we just repeated the virtuous cycle again. We suggested to the mathematicians, hey, maybe the short geodesic or the injectivity radius might help you to fix the conjecture, to make it work. And it turns out that was all that was needed, really. The mathematicians realized that using the injectivity radius, they were able to patch up this upper bound and get a formula that they were actually able to prove. Okay? So this is actually a theorem, a formula we've been able to derive. And in case you thought, you know, we had to cherry pick and choose this injectivity radius, sometime later, mathematicians also took the short geodesic and made a similar equivalent version of this theorem that uses the short geodesic. So it's not that we had to like stab in the dark and choose it randomly. If we went with the short geodesic, we would have succeeded as well. And both theorems are available in the mathematical paper that we released. Okay? And basically, this formula, this epiphany that we had in collaboration with the AI world and the pure mathematician world was highlighted on the cover of our Nature work. You can see this equation is basically the place where the AI world with their wiring and chips and so on intersects with the world of the pure mathematician with their you know, pencil writing and grids and coffee stains and so on. Yeah, the cover of the Nature paper actually has a coffee stain on it, so now you know. Okay, so this was the first work that I was only tangentially involved in, and it involved a very simple kind of intervention of a machine learning model. Now I'd like to tell you a bit more about the part of the math project that I was personally involved in as one of the lead modelers, because it involved graph neural networks and graph representation learning, which I mentioned to you earlier is an area I'm very excited about. And specifically, the objects we studied here were these permutations. These are just simple operations that take a set of elements and return that set of elements in a different order, right? And you can often numerically code them. So in this case, the 3, 2, 4, 1, 5 tells you element A ended up in the third place, element B in the second place, C in the fourth place, and so on and so forth, right? And specifically in this space, we looked at some interesting graphs where the nodes were permutations. So interesting networks where nodes are permutations, and you connect them together if you can obtain one from the other by a swap or something like this. And we wanted to study the so-called combinatorial invariance conjecture. This was a 50-year-old unsolved problem in representation theory, a very important fundamental problem in the area. And essentially, it asks, can you take this structure of a graph and compute the coefficients of some polynomial, which also depends on the two permutations that are at the top and the bottom, okay? So there are these two mathematical objects, a graph and a polynomial, and there's a long-standing conjecture saying that I can compute the polynomial from the graph, but nobody knew how to do it, okay? And I just want to offer you one possible explanation for why this problem was not attacked properly for 50 years, okay? Even though mathematicians knew about it and they could use computers to generate many examples of these graphs and polynomials, they just couldn't find the regularity because this here, as I said, is a polynomial. So it can have any power of q, right? You can have q squared, q to the 3, so on and so forth. So you might be asking yourself, what's the smallest graph where q squared starts to appear? It's this graph, okay? And as our mathematical collaborator remarked here in pencil, this is one of the easiest examples, okay? And I don't have a background in representation theory or graph theory, but I cannot tell any meaningful patterns happening here. It's just too big for me to make sense of it. And I imagine it's a similar problem for the mathematicians because you can imagine it gets even more complicated when you include q to the third, q to the fourth, and you need to make a formula that works for all powers of q, right? So even though you can generate arbitrary examples, it's really hard to think about what happens here. It's almost like you need a kind of precision microscope to tell you which parts of this graph are most important. Well, AI to the rescue, right? We tried to train one of these models that I know and love, the graph neural network, to predict the polynomial from the graph structure, okay? And it turned out that this graph neural network had a pretty good score, about 65% accuracy for many of the coefficients, which was already quite exciting for our collaborator because nobody really knew of any algorithms that would properly compute these coefficients in the first place. So this was very encouraging for the mathematician. And now we tried to investigate together with them what were the meaningful parts of this graph that led to that confident prediction, okay? And in this case, because we're analyzing a graph structure, what our proposals would be some particular nodes and edges that were most important for the prediction, okay? And basically then we sent a bunch of subgraphs to the mathematician. Now to us, these subgraphs looked like garbled nonsense. We really couldn't make sense of what the model found most important, okay? But given to a top expert in this domain 2 weeks to stare at these graphs, he was actually able to detect the signal in the ton of noise. And he actually realized that these kinds of diamond structures around the root node seem to appear again and again and again concealed in a ton of noise, okay? So he made a fantastic observation, actually, because then we tried to complete the virtuous cycle and to add this graph neural network some extra input features telling it where the diamonds are, so it doesn't have to hunt for them by itself. And with that extra information, our accuracy skyrocketed to 99, 98%, okay? So this was a super encouraging moment for the mathematician because not only we had a highly predictive model, we knew exactly what we had to add to the model to make it have that high accuracy. Like we knew these diamonds are likely to be very important, okay? And okay, now we can ask the network again, what were the patterns that led to this 98% accuracy, right? And as I told you, these edges in the graph correspond to different swaps of elements in that set. So we actually just plotted a simple heat map. This is the group of 9 element sets. So elements are numbered from 0 to 8. And I asked which edges were the most important to this graph neural network. And as I said, each edge swaps 2 elements. So here, this block here means how often does the network want to take the swap of element 0 and element 8, right? And what you can notice here, well, how this heat map is structured, it tends to really prefer swapping element 0 and really prefer swapping element 8. These rows and columns are very high heat, right? And that led our math collaborator to realize that these kinds of extremal swaps are what's very important for the formula. And the significance that this ended up having in our formula was so important that it led to one of our reviewers of the Nature paper to say, the feeling that these extremal swaps seem to play a crucial role is one they would have expected only from a handful of great world experts in representation theory, and it was such a human suggestion that it gave them goosebumps, I quote. So basically, even with a very simple machine learning intervention plus heat map, you can end up with goosebump-inducing results. So I hope this shows just as an insight to the future, what we might be able to achieve with more sophisticated explainability methods. So, based on these insights of the diamonds and the extremal swaps, Jordi Williamson was able to come up with a conjecture that says you can actually compute this polynomial by reducing the problem to a smaller subgraph called an inductive piece, from which we pre-computed the solution. And this sort of hypercube piece, well, this hypercube is not very interesting because it's just a square, but it can be a more complicated structure. And based on these two, you can compute the polynomial. In fact, we were able to prove a theorem that for every graph I give you like this, there must exist one canonical decomposition into these two parts such that I can compute the polynomial. Now, you might be wondering, does this solve the combinatorial invariance conjecture? Unfortunately, it doesn't, because it says there exists a decomposition that works. There could be many decompositions, and we don't tell you how to find the right one, right? So we did what a machine learning person would do. We wanted to build a data set of all the decompositions and whether or not they get the right answer. So we can do like a simple classification problem. And yeah, what do you think happened? Every single one of those decompositions worked. So from an AI standpoint, we had a very imbalanced data set, I guess. But from a mathematics standpoint, we were able to just make a conjecture that no matter how you split this graph into the two parts, you're going to get the correct answer. We haven't been able to prove this yet, but if we're able to prove it, this would settle the conjecture once and for all. And in our paper, which recently got accepted into the mathematical top-tier journal of representation theory, Jordi actually gives a pretty good proof sketch for how one might be able to try to prove this. And you know, if any of you are minded in representation theory, this could be a very interesting challenge that we have now enabled through the use of AI-discovered patterns. So I must stress, for 50 years, nobody knew anything in terms of interesting structure in this problem. Over the space of a year and a half of carefully guided AI interventions, we discovered these three key structures that now appear to make the problem within reach. So now you might be asking, now that we've done these measurable impacts in two areas of mathematics and even published some of this at relevant top-tier mathematical journals, you might be wondering, what next? Well, obviously, we want to try to take these ideas and spread them apart to try to solve more interesting scientific problems in mathematics or otherwise, because we believe similar AI interventions could mean a lot for many related areas of science. But actually, what I wanted to take the last few minutes of this talk to kind of highlight to you is what can happen if we go in the opposite direction, basically. What if we use an intervention from a mathematician to help us building AI systems? And I'm going to present to you this expander graph propagation paper that we just recently submitted to a top-tier AI conference, and it's basically an example of an amazing thing that can happen when you speak to a mathematician. So to give you a bit of background, one big problem that we have in graph representation learning that I mentioned at the beginning is a booming area of machine learning, is that when you aggregate information over a graph, a single node must store potentially a huge amount of context of all the nodes that are around it in the network. So there's a lot of pressure for this node to store all that knowledge properly, okay? And it's illustrated in this particular case of a problem where you have these green nodes that have different numbers of neighbors, and you have a question mark node. You need to match it with the node that has the same number of neighbors. So in this case, the label would have to be C, because they both have two blue nodes neighbors. But you put a huge, complicated graph structure in the middle to make it hard for information from here to travel here, okay? And most graph neural networks cannot even fit the training data for this problem properly, let alone more complicated data. And, well, with very brief intervention conversations with Mark Lackenby, who is one of our math collaborators, and also in collaboration with Andrea Deac, we have been able to come up with this expander graph propagation paper, which seemingly solves all of these bottleneck problems in a somewhat elegant and better way than previous approaches. And how do we do it? Basically, we relax the bottlenecks by propagating information over these interesting expander graph structures, which are very well known and understood in mathematics, very easy to compute. But for us in machine learning, we just did not have the knowledge of this obscure area of maths. And I basically mentioned to Mark, hey, we have this problem with bottlenecks, and he immediately told me there are these expander graphs that have no bottlenecks, provably. So if you just propagate information over them, that's going to fix your problem. And the amazing part is that then he was able to give me a 2-page LaTeX document with all the theorems and all the results I'm going to need, so I don't have to do all of that mathematics by myself. And very often ideas that in machine learning it takes us 2-3 years to discover, a mathematician can just, snap their fingers and give it to us, right? So, and remarkably, beyond just being very well theoretically motivated, it works very well in practice. Very simple intervention to a state-of-the-art baseline machine learning model with this expander graph to propagate information, and we significantly improve performance on 3 interesting data sets in computational chemistry and code analysis. So I hope this gives you a very good idea of how not only should we try to help intervene in the day-to-day work of mathematicians, we should also just generally chat to mathematicians about our problems, and their interventions can help us progress a lot faster than we otherwise would. Thank you so much for listening and for inviting me. I'd be very happy to take questions. If you want to contact me afterwards, my email and my social networks are here as well. And I'd like to just once again thank all of my collaborators from the DeepMind project, from Oxford and Sydney, and Andrea from Mila as well. Thank you so much.